This kind of data is gathered in a fraction of the time compared to before, so I think many of the records we have in the current-day universe are going to be broken soon. It has been 2 years since NASA's James Webb Telescope gave us a stunning first look at the depths of our universe. Our universe is growing at an abnormal rate. The universe was found to be expanding like a balloon and speeding away from each other, first observed by astronomer Edwin Hubble about a century ago. Our present-day best theory for the Big Bang's origins is based on tracing that expansion backward in time. However, a concerning gap has been expanding in this depiction for the last 10 years. The rate of the cosmos expansion denoted as the Hubble constant differs substantially depending on the vantage point from which astronomers observe it. Launched in late 2021, the James Webb Space Telescope was the most technologically advanced telescope ever made. Scientists hoped it would finally resolve the debate, but no agreement has been reached so far. We may need to rewrite all the textbooks, according to a Nobel Prize-winning physicist from Johns Hopkins University who claims that fresh data obtained by James Webb recently proved that our previous view of the universe was entirely incorrect. Come investigate with us what's happening. There was a Big Bang at the beginning of the cosmos according to the most popular theory. The universe came into being in a flash, a churning plasma stew of matter and antimatter particles that spontaneously expanded and destroyed one another upon contact. Scientists believe the cosmos was saved from instant self-destruction because for some reason more matter than antimatter was formed, even though the matter and antimatter within this plasma should have entirely consumed each other if left to their own devices. Gravity squeezed and heated plasma pockets to the point where baryon acoustic oscillations, sound waves that move slightly faster than light, rippled across their surfaces. The early cosmos expanded like a balloon, trapping a tiny portion of matter while its high energy densities strained spacetime and kept the rest out of harm's way. The conventional wisdom holds that the universe's first galaxies formed when visible light interacting with ordinary matter solidified around clusters of invisible dark matter with the help of a huge cosmic web that linked them all. Initially, the expansion rate of the cosmos slowed down because its energy density dropped as its contents expanded, but then at an accelerating rate galaxies started to recede again about 5 billion years ago. Dark energy, another unseen and enigmatic force, was to blame. A cosmological constant, or inflationary energy, that is constant in all locations and times and embedded in the expanding fabric of spacetime, is the most popular and straightforward description of dark energy. As part of his theory of general relativity, Einstein gave it the moniker lambda. Over time, dark energy density became the most significant factor in the expansion of our universe, while overall matter density decreased. The energy densities of light, dark energy, ordinary matter, and dark matter determine the maximum speed at which the universe may expand. The lambda cold dark matter (LCDM) model of cosmology uses them as well. It charts the expansion of the universe and foretells its demise, with matter becoming so thin that it undergoes a thermal death known as the Big Freeze. Although many of the model's forecasts have been accurate, this is where things start to go wrong. Astronomers have been hunting for dark matter and dark energy but have come up empty-handed so far. According to Ofer Lohov, an astronomy professor at University College London who is involved in galaxy surveys of dark energy, the embarrassing fact is we don't understand the last two of them. He continued, most people agree that the universe's present composition is 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. However, a more serious threat to the LCDM model has emerged. The universe appears to be expanding at different rates depending on the method astronomers use. This discrepancy, called the Hubble tension, reveals that the early cosmos is expanding at a far quicker rate than LCDM predicts according to methods that look into the past. Numerous observations have confirmed and validated these procedures. It requires more than just a radar gun to measure the expansion of the cosmos. An artifact of the early cosmos created only 380,000 years after the Big Bang, the so-called cosmic microwave background, CMB, provides the baseline for the first approach at quantifying this expansion. From 2009 to 2013, the Planck satellite of the European Space Agency mapped this imprint visible across the sky to determine a Hubble constant with an uncertainty of less than 1%. This cosmic newborn image shows a nearly uniform cosmos with hotter and colder regions indicating regions of higher and lower matter density respectively, caused by baryon acoustic vibrations that cause the universe to expand outward. Galaxies formed at the intersections of the crisscrossing strands that this soap bubble structure eventually expanded into, forming the cosmic web. The Planck spacecraft studied these ripples, and cosmologists deduced the masses of dark matter, regular matter, and a value for the cosmological constant also known as dark energy. The standard model, when fed these results, gave a Hubble constant of about 67 km per megaparsec. For now, let's hold off on this number. A galaxy 1 megaparsec from Earth will recede from our view at 67 km per second, while our galaxy will do the same. The recession reaches a maximum speed of 1,340 km per second at 20 megaparsecs and continues to expand exponentially after that. The speed of light is less than the distance at which a galaxy will recede from Earth, which is 4,475 megaparsecs. Alternatively, we can use pulsating stars or Cepheid variables, which are dying stars with helium gas outer layers. These stars' radiation causes them to expand and contract regularly, flickering like faraway signal lamps. We can use this information to calculate the rate of expansion. Astronomer Henrietta Swan-Leavitt discovered in 1912 that Cepheid flicker rates were directly proportional to a star's brightness, allowing for the measurement of absolute brightness and, by extension, distance. This discovery was so revolutionary that it made Cepheids the de facto standard candles for gauging the vastness of the cosmos. By stringing together observations of pulsating Cepheids, astronomers can build cosmic distance ladders, with each rung allowing them to travel across time. An astronomer from the University of Chicago, Wendy Friedman, described it as one of the most accurate means that astronomers have today for measuring distances. By selecting nearby Cepheids and comparing their distance determined by pulsating light with that discovered by geometry, astronomers create the first rung of a distance ladder. Cepheid measurements alone are used to add the following rungs as the cosmos continues to expand, and the light from stars and supernovae at different distances on each rung gets redshifted, moving to longer, redder wavelengths. This process is then compared by astronomers, resulting in an exact value for the Hubble constant. In 2019, Rees and colleagues utilized this method to train the Hubble Space Telescope on the Large Magellanic Cloud, a neighboring galaxy to the Milky Way. The outcome was catastrophic, showing an expansion rate of 74 km per second per megaparsec, which is mathematically impossible. Cosmologists have begun referring to the apparent discrepancy between the two measurements as the Hubble tension. When contrasted with the Planck measurement, no one has a clue why this is happening, although some theories propose novel physical principles to resolve the seeming paradox. One theory suggests that Cepheid variables located at the base of the cosmic distance ladder could be the source of the measurement inaccuracy. New observations taken with the James Webb Space Telescope of 5 galaxies that house over 1,000 Cepheid variables have eliminated this potential mistake. With its superior resolution, James Webb's infrared vision can slice through interstellar dust, revealing the Cepheid variables in all their glory. Adam Rees of Johns Hopkins University headed the astronomical team that used these Webb observations to confirm that the initial measurements taken by Hubble were accurate. Among the 5 galaxies James Webb studied, 8 Type Ia supernovae have been ejected in the last few decades. The farthest of these galaxies is NGC 5468, which is 130 million light-years away. Following the Cepheids on the cosmic distance ladder are these supernovae, which indicate the demise of white dwarfs and possess a standardizable luminosity curve. They also confirmed that the various assessments of the Hubble constant provide an inconsistency. The fundamental conflict in cosmology, therefore, will not go away. We need to determine if something is lacking in our understanding of the universe's beginning and its present state. Now that measurement errors have been eliminated, the fascinating and real possibility remains that we have misinterpreted the cosmos. Although searching for new physics that could explain the discrepancy seems to be the best course of action at the moment, some scientists believe Earth might be close to the middle of a supervoid, a vast area with below-average density about 2 billion light-years across, where galaxies tend to move outward. Behavior apart from dark matter, this is an alternate gravity hypothesis. We will probably have to expand our knowledge of the cosmos in order to resolve the Hubble tension. This is an exciting but unproven mix of ideas to get a desired result. It's easy to make a model more complicated, but that complexity will just cause additional problems in the end. This approach achieves the desired outcome of alleviating the Hubble tension, but to a lesser extent. However, a great deal of intricacy is required to reach that point due to the difficulty in determining the universe's total density at such small scales. Not all astronomers acknowledge the existence of the local supervoid. Although the supervoid defies conventional cosmological theory, not all astronomers hold this view. It might make perfect sense even if it doesn't rely on quantum mechanics. Supernovae might be mostly unaffected by the existence of a supervoid. According to some scientists, this might lead us to misjudge the Hubble constant. Plus, very few astronomers think man has any real legs as a theory. Actually, most cosmologists and astronomers don't think man works at all, particularly because it still needs dark matter to account for all the many kinds of structures we see in the cosmos. The concept of sterile neutrinos, which is essential to this paradigm, is still in its infancy and is, while intriguing, not based on any real evidence. Last but not least, any reasonable cosmological theory would have to account for the Milky Way's location far from the local supervoid's periphery if this scenario were to hold. This investigation has the potential to yield useful results and provide a novel concept that might alleviate the Hubble stress. For the time being, the results are predicated on elementary universe-building models. In the end, the facts will determine the outcome, but we will proceed by applying this principle to a more accurate simulation. However, while we wait, let's return to James Webb. 2 years have passed since the James Webb Space Telescope began transmitting photos back to Earth, and NASA recently commemorated this milestone. Over the past 2 years, James Webb has not only provided scientists with data that has transformed our understanding of the universe, but it has also consistently delivered photographs of breathtaking beauty. The most distant galaxies ever seen by humans have been discovered by the observatory. Some of these galaxies are so far away that they were around when the universe, which is 13.8 billion years old, was only 300 million years old. Also detected by the most powerful satellite telescope to date are quasars driven by supermassive black holes that were active in the universe within a billion years of the Big Bang. Cosmologists now face a huge conundrum in trying to explain the rapid and immense growth of these giants in the early cosmos. The light from distant galaxies that has been bent and widened over billions of years due to the universe's expansion is easily detectable by the Webb telescope. That's the secret to the telescope's ability to spot quasars and young galaxies. Even closer to home in our solar system in particular, scientists weren't anticipating the space telescope to be so helpful. A pleasant surprise that was. All astronomers were worried that the powerful space telescope might be obscured by nearby objects, but instead it has seen familiar solar system giants like Jupiter in a whole new light. In a statement issued by NASA Administrator Bill Nelson, since President Biden and Vice President Harris unveiled the first image from the James Webb Space Telescope 2 years ago, Webb has continued to unlock the mysteries of the universe with remarkable images from the corners of the cosmos going back nearly to the beginning of time. James Webb's capabilities are shedding new light on our celestial surroundings and inspiring future generations of scientists, astronomers, and explorers. In addition, NASA has just revealed another breathtaking image captured by the groundbreaking James Webb Space Telescope, marking 2 years since the telescope started transmitting photos back to Earth. The object, known as ARP-142, which resembles a cosmic penguin clutching its cosmic egg, is actually a composite of 2 galaxies that have been observed in the second anniversary Webb photograph. The latest image, appropriately commemorating James Webb's 2 years of scientific accomplishments, is a 2-for-2. The penguin and egg seen in ARP-142 are 2 interacting galaxies situated about 326 million light-years away from Earth in the Hydra constellation. It has been seen previously, but never with the clarity that this telescope image provides. The new picture shows ARP-142 in infrared light as viewed by MIRI and James Webb's NIRCam. The penguin is NGC 2936, a twisted spiral galaxy, while the egg is NGC 2937, another stellar object. Nearly 100,000 light-years separate the 2 galaxies, which is very near when viewed through the galactic perspective. As an illustration, the Milky Way galaxy and its nearest neighbor, the Andromeda galaxy, are around 2.5 million light-years distant. One galaxy couldn't just eat the other because the penguin and its egg are about the same mass. Obviously, NASA couldn't host a celebration for James Webb with just 2 galaxies in attendance. Above the penguin and egg picture in the upper right, you can see the galaxy PGC 112371, located only 100 million light-years from Earth. This young galaxy is teeming with blue newborn stars. The blue swoop provides an edge and view of it. Are producing stars up to 5,000 times faster than the Milky Way. Star-forming gas being directed into PJ 3082's galaxy by its satellites may feed the quasar as it expands into a supermassive black hole. Additionally, recent observations of a white dwarf star in the process of cannibalizing its own planetary system were made public by the James Webb Telescope. What are your thoughts on this? Do you believe man will eventually resolve the Hubble tension issue, or do you agree with NASA that the James Webb Space